This is the Math 2 lesson summary video for Lesson 1, Leaping Lizards. In this video, we will be looking at the task Leaping Lizards. The purpose of this task is to develop more precise definitions and discover properties of the three types of rigid motion transformations: translations or slides, reflections or flips, and rotations or turns. By the end of this task, you should be able to define and identify a rigid transformation or isometry, define and identify a pre-image and an image, create a rigid motion transformation of a geometric figure, describe the rigid motion transformation with words and a mapping rule, and describe the properties of each rigid motion transformation. Before we begin performing transformations with our lizard, we need to review a few important key vocabulary words. A pre-image is an image before a transformation occurs. It is a starting point and is indicated with a letter, such as P. An image is a figure after a transformation has occurred, or an ending point. It is indicated with a letter such as P prime. The prime looks like an apostrophe next to the letter. The third vocabulary word we need to review is rigid motion or isometry. A rigid motion is the process of moving a geometric object from one place to another without changing its size or shape. So an isometry will produce congruent figures. Reflections, rotations, and translations are the three rigid motions that we will investigate today. Part 1 of this task is to translate the original lizard so that the point of his nose is located at the ordered pair 2420, making the lizard appear to be sunbathing on the rock. You can do this with patty paper or by counting. Some students in class recognized that the tip of the nose had to move to the right and up in order to be positioned on the rock. It was discovered that the tip of the nose would have to move 12 units to the right and 8 units up. Since a translation is a rigid motion, all points on the lizard have to move the same distance and the same direction. So we could count each point and move it 12 units to the right and 8 units up. Other students recognized that the points would have the same relation to each other as they had in the pre-image. So some students, instead of moving each point 12 units to the right and 8 units up, would look at the relation between the tip of the nose and the point on his front foot. They recognized it was 2 units to the right and about 4 units up. This method also works because the transformation of a translation preserves distance and angle measure. Other students used patty paper. Patty paper is a tool that allows us to trace an image. Lay the patty paper over the diagram and trace the points onto the patty paper and trace the lizard onto the patty paper. One of the tips is to also trace a part of the coordinate plane onto the patty paper, so when you slide the patty paper, you know that all of the points are still lined up vertically and horizontally. So we're going to slide the lizard to the right 12 units and up 8 units until the nose coincides with the point 2420. Now that we've looked at a couple of different ways to perform a translation, we can provide a more formal definition. A translation is a rigid motion transformation, or isometry, that moves every point of the shape the same distance and the same direction. There are a few different ways that we can represent a translation in the coordinate plane. For the lazy lizard, we could use words or a verbal description to describe the movement. We could say that the lizard was translated to the right 12 units and up 8 units. When you provide words or a verbal description, it is important to include the type of transformation as well as the magnitude and direction. We can also use a mapping rule or an algebraic rule. The mapping rule is an algebraic rule that is applied to the input or the pre-image points to create the output or the image points. During class, some students describe the movement of the lizard as a diagonal motion. The students were describing the segments connecting the corresponding pre-image points to the image points. We can further define a translation as a movement of points a specified distance along parallel lines. Parallel lines all share the same slope. Part 2 of the task is lunging lizard. In lunging lizard, we are asked to rotate the lizard 90 degrees about point A at 12:7, so it looks like the lizard is diving into the puddle of mud. In the directions, it tells us the type of transformation, which is a rotation, and it gives us the angle of rotation, 90 degrees, but it doesn't specify a direction. If a direction is not specified, the default direction is counterclockwise. In class, some students used the patty paper from the lazy lizard to rotate the lizard 90 degrees counterclockwise. The students had traced the lizard onto the patty paper and had also traced the line x equals 12 onto the patty paper, as well as the point 12:7 since it's the center of rotation. Since 12:7 is point A, the center of rotation, that point will remain fixed and the lizard will rotate around that point. "90 degrees is 1/4 of a complete turn. If we connect each pre-image point with its corresponding image point, we can see that each point moved along a circular arc, the same direction, which is counterclockwise, and through the same angle of rotation, which was 90 degrees. We can connect the pre-image point to the center of rotation to illustrate the 90-degree angle of rotation. After performing the rotation to create the lunging lizard, we can write a more precise definition for the rigid motion of rotation. Rotation is an isometry that moves points in the same direction along a circular arc or concentric circles with a specified center and angle. A property of a rotation is that the segments formed when connecting a pre-image point to the center and the corresponding image point to the center are congruent. These segments are radii of a circle. The final part of the task is an investigation on reflections. Let's Get Away lizard reflects the lizard over the line x equals 23 to make the lizard appear to be turning around to run away from a predator. The line x equals 23 is a vertical line. The lizard will be flipping over the line. We can use patty paper to help us visualize how the lizard should look when he flips over the line. When we compare the pre-image and the image, we can see that the pre-image and the image are equidistant from the line of reflection. That means they're the same distance away from the line of reflection. Just like with the translation and the rotation, we're going to connect the pre-image point with the corresponding image points. We can see that the segments connecting the corresponding pre-image and image points are parallel, like the translation. Unlike the translation, these segments are not congruent to each other. We can see that they are equidistant from the line of reflection. So if we look at the point on the lizard's foot, it is 1, 2, 3, 4, 5, 6, 7, 8, 9 units from the line of reflection. And the corresponding image point is 1, 2, 3, 4, 5, 6, 7, 8, 9 units from the line of reflection. This is true for all of the corresponding pre-image and image points. The line of reflection is passing through the midpoint of each segment connecting the pre-image and its corresponding image. Additionally, we can see that the line of reflection and the segments connecting the pre-image to the image are perpendicular. The line of reflection was a vertical line, and the segment connecting the pre-image to the image is horizontal. We could also verify this right angle by finding the slopes of the line of reflection and the segment connecting the pre-image to the image, or we could create a right triangle and use the Pythagorean theorem. Since the line of reflection passes through the midpoint of each of the segments, and it is perpendicular to each of the segments, we can call the line of reflection the perpendicular bisector of the segments connecting the pre-image points to the corresponding image points. Now that we have performed a reflection for Let's Get Away lizard, we can write a more precise definition for reflection. A reflection is a rigid motion that moves points across a specified line of reflection to produce an image. One of the important properties of reflection is that the line of reflection is the perpendicular bisector of each line segment connecting the corresponding pre-image and image points. For the final part of the task, Leaping Lizard, we are asked to reflect the lizard about the given line, y equals 1/2 x plus 16, so it looks like the lizard is doing a backflip over the cactus. We can use patty paper to help us flip the lizard over the line of reflection. After we have drawn the image and segments connecting the pre-image point to its corresponding image point, we can see some of the properties of reflection. The slope of the line of reflection was 1/2. If we find the slope of the segment connecting the pre-image point of the lizard's nose to the image point of the lizard's nose, we will find that that slope is -2. This is further evidence that the line of reflection and the segment connecting the pre-image point to its corresponding image point are perpendicular. We know this because perpendicular lines have slopes that are opposite reciprocals of each other. We could also use the distance formula or the Pythagorean theorem to verify that the distance from the lizard's pre-image point nose to the line of reflection is the same as the distance from the image point of the nose to the line of reflection. This concludes the Leaping Lizards task. If you need more help on the Ready, Set, Go homework for this task, please remember to check the Canvas Student Support site.